At the beginning of this course, we talked very briefly about how audio could be represented by numbers. Now we're going to take a much more in-depth look at sampling theory, which is the formal description and analysis of how continuous signals can be represented by discrete samples and converted back and forth. There's a lot of interesting information here, and I hope you enjoy it. So we're really concerned with the trip from analog to digital and back, from continuous signals to discrete digital samples. We do this with analog to digital conversion and digital to analog conversion. And there are quite a number of steps and concepts involved. So we're going to start out with a very intuitive approach and look at what's going on. Then we're going to have to step back and study the frequency domain and the Fourier transform in order to sort of build up an arsenal of analysis tools and concepts to let us really analyze what's going on. Then we can present the principal results of sampling theory and derive some practical results from that. So we'll start with intuition. Okay, we live in an analog world. We can talk about the tides coming in and going out, the height of snowfall, the velocity of a kid on a tricycle, the altitude of a balloon or wind speed. All of these are continuous analog quantities. So let's look at this curve. Is this continuous or discrete? Well, this is how we draw continuous things on a computer screen, but of course the computer screen is made of pixels, and the pixels have finite resolution in terms of brightness. So in some sense, this is actually a discrete image. It's just sampled in terms of pixels. When we sample things, we go from continuous to discrete individual values in 2 dimensions. So first of all, there are discrete amplitude measurements. This is the vertical or y-axis, because we're converting what we think of as continuous or maybe real numbers into integer samples with finite resolution. There's also a discrete aspect to the horizontal, the x-axis or the time axis, because we're taking not samples infinitely often, but only periodically at discrete time points. So when we digitize a continuous function or signal like this, we're first of all measuring the signal at discrete time points, and then we're quantizing the times in the vertical axis to get integer values. So some questions arise from this. First of all, what sample rate should we use, and why does it matter? How many bits per sample should we use, and why does that matter? Then the question of interpolation. How can we interpolate samples to recover the sampled signal? And what's the effect of rounding to the nearest integer sample value? And finally, how do we actually convert analog to and from digital? So these are the questions that are answered by sampling theory, and we will get to them in this talk. But before we do that, we need to get some tools together, and primarily an understanding of the frequency spectrum. So to introduce that, let's start with this signal again. Any signal can be represented as the sum of sinusoidal components called partials. If we take these sinusoids shown here and form their sum, and taking the sum just means at every point in time you take the value of each one of these signals and add those values together, and that's the value at that time point in the summation. Okay, and when you sum these signals shown here, you get the signal shown at the bottom. Now, what do we mean by a sinusoidal component? Well, sinusoids have, first of all, phase. So if you look at these two signals very carefully, they're not identical because the upper one, it looks like, is shifted very slightly to the right relative to the lower one. Okay, so that time shift is called phase. The second aspect is frequency. That's what is the repetition rate. Every sinusoid has a frequency. And finally, we have amplitude. We could have a small amplitude signal or a large amplitude signal, so that's another parameter. So we have three parameters. From left to right here, A is amplitude, omega is frequency, and phi is phase. And so this is the mathematical formula for a sinusoidal partial. It's the amplitude times sine of omega t plus phi. Now, Fourier transform. Our goal is to transform a function of time representation of a signal to a function of frequency representation. Essentially, what we're going to do is decompose the signal into a sum of sinusoidal partials. In fact, we express the time function as an infinite sum of sinusoids, and we express this infinite sum as a function from frequency to amplitude. So in other words, I'll give you a frequency like 100 hertz, and you tell me, okay, at 100 hertz, the amplitude is 0.01. So a function from frequency to amplitude, and that's what the Fourier transform gives us. So this is the Fourier transform. The way it's expressed here, there are two functions. There's the real part and the imaginary part, and that's because there's not only at a given frequency, you not only have an amplitude, but you have a phase. So there are really two parameters, so we need two functions. Notice that these are expressed as integrals. F of t is the function that we're analyzing or taking the transform of, and we do this infinite integral. Omega is remember, our goal is to get a function of frequency that gives us an amplitude. So the function is a function of omega, the frequency, and the amplitude is this computed by this integral. Okay, so what about phase? I just showed you these two functions, a real part and an imaginary part. What's that got to do with phase? Well, the Fourier analysis computes these two amplitudes, real and imaginary, or r of omega, x of omega. And we can use trigonometry to convert that from real and imaginary to amplitude and angle. So the amplitude represented by r of omega and x of omega is this equation down here. We take r squared plus x squared, take the square root, and that's the amplitude. Or we could say the a as a function of omega is r as a function of omega squared plus x of omega squared, and take the square root of that. Same thing. Now, the phase is the arctangent of x over r. Or if you like seeing the omega parameter, frequency parameter in there, we take x of omega divided by r of omega, take the arctangent, and that gives us phi of omega. So at every frequency, there's both an amplitude A and a phase phi. Just equivalent to the real and imaginary parameters. All right, another thing that is commonly done is rather than dealing with two functions, the real part and the imaginary part, we can just add them together as a real and imaginary number to form a complex number. So a complex number is just a pair of reals where one represents the real number axis, one represents the imaginary number axis. And imaginary, just to be clear, is the square root of -1 is I. Or here it's written as j, and that gives us a different coordinate. Okay, so we can write f, the Fourier transform, is a function of omega, and it's equal to r of omega plus j times x of omega. So we can put the real and imaginary parts together to make one complex valued Fourier transform function. If we do that, just using a little math, we can, if we add r of omega plus j x of omega, again, let me remind you, j here is the square root of -1. Electrical engineers like to use j. You probably were taught to use I in school as the square root of -1. The reason electrical engineers use j is because I means current. It's already taken. So, but it's the same thing. Okay, so if we take r of omega plus j x of omega, and we form the sum of these two integrals, and effectively what happens is we get f of t times cosine omega t minus j sine omega t as the thing that we're integrating by, and that's equivalent to e to the minus j omega t. This is a trig identity. If you don't know it, it's not too important. That's why I presented this without using complex numbers. But the cool thing about using complex numbers is you get to combine the real and the imaginary parts into one complex number, and so then you only have one equation instead of two. Now, what does this mean? These sinusoids are orthogonal to one another. What does orthogonal mean? Well, the simplest example I can give is in Cartesian coordinates or on a map, you have north-south and you have east-west as different axes. So if you know how far north you are and how far west you are, you can add those together because they're independent and come up with a location. Well, sound is kind of like that, only on with infinitely many coordinates, not just north, south, east, west, but infinite number of different, every frequency is a coordinate, and so there are infinitely many frequencies, so we have an infinite coordinate system. So the amplitudes of all these coordinates added together gives us a location in this infinite space, and every location corresponds to a sound. And the important thing here, the reason for bringing this up, is that just as you can decompose any location on a map into a certain amount north and a certain amount west, you can decompose any sound into a certain amount at 100 hertz and a certain amount at 100.1 hertz, and at all these infinite frequencies, the amplitudes are uniquely determined. So there's a unique linear combination of these sinusoids, which are called basis vectors. Because of that, you can take the Fourier transform of a signal and get a unique result, and that unique result can also be inverse transformed back into a sound, and you'll get exactly the same sound back. So this representation of different amplitudes at different frequencies is called the frequency domain, just like we talk about the time. The signal as a function of time is in the time domain. So what does the frequency domain mean? Well, you've probably seen graphical equalizers or maybe spectrum analyzers that give you amplitudes at different frequencies, and that's a good kind of intuitive representation of what's going on in the frequency domain. We're decomposing a sound into components at different frequencies. How do we do that? Well, of course, I showed you the math, so we're forming these integrals. But why integrals, and why are we multiplying by cosines and sines? And what's going on here? Essentially, what happens is when you multiply by a cosine or sine and take the integral, you're constructing a filter. And so really the frequency analysis is essentially taking a filter bank, putting a filter at each narrow range of frequencies and measuring the amplitude that comes out. Okay, so here's a very simplified diagram of a filter bank. A sound comes in, and for each channel or each frequency, an amplitude comes out. And if we plot the values that come out here, we get this thing called the spectrum. So stop for a moment and see if you can identify what these axes are. What's the horizontal axis? What's the vertical axis? Okay, well, I'll tell you. Check your answer. The horizontal axis is frequency, all right, because we're at each channel is filtering a different frequency, so we're plotting things as a function of frequency. And the vertical axis is amplitude or energy. How much of the signal is getting through this filter at different frequencies. So the spectrum is a function of frequency, and it gives you the amplitude at each frequency. Commonly, we only consider the amplitude part of the spectrum. The complete Fourier transform, as we have said, has phase as well as amplitude. But first of all, phase is something that we are not very sensitive to with our hearing. So phase changes really make almost no difference to a sound, even relative phase changes. And so a lot of times we just ignore them. And so that allows us to plot spectra as amplitude versus frequency. And here are some spectra that should make sense to you. If you've ever seen a tuning fork, you hit the tuning fork and it mostly produces a sinusoid. So when you analyze that, you get no energy except at one frequency where that sinusoid exists. And so we plot that as a single sinusoidal component at one location. Typically, tuning forks are tuned to 440 hertz. All right, so this is the spectrum of the sound produced by a tuning fork. We can talk about the spectra of real signals, and in fact, I have running here a piece of software called Audio Explorer, and it is in real time taking whatever comes into the microphone, computing the spectrum of a short time and plotting it. Now this is a little misleading because this spectrum that you see is obviously changing as a function of time, and a true Fourier transform integrates out all time for a sound. It's more or less an abstract construction, but I want to be clear and emphasize that the Fourier transform, as I've explained it, does not have a time varying component. It's only a function of frequency. Okay, and we will talk about what's going on in this display, which is called a short-term Fourier transform, a little bit later, but they're similar, and this should give you an idea of some things. So first of all, let me make some noise. I'll try to make kind of uniform noise by with air. So and watch what happens to the spectrum. Okay, the spectrum is very chaotic and very random, and you notice that there's a lot of energy at a lot of different frequencies. You know, there's energy all over the place, and that's characteristic of noise. It's very, very broadband. On the other hand, I have this little koto-like instrument, and if I pluck a string here, well, the spectrum is kind of fleeting, but you see that there are very specific singular components. They're all happen to be harmonics of one another. And we've talked about harmonic spectra before, so now you can actually see them. So those peaks are the harmonics that we've been talking about that exist in periodic signals that have pitch. Okay, this is kind of fleeting, so another thing that I can do is I happen to be a trumpet player, and let me try to produce a more or less steady, continuous sound, and you'll be able to see a set of harmonics, set of sinusoids that constitute this single tone. Well, let me turn the amplitude down a little here. Still a little high, but okay, so you can see those sinusoidal components. Let me get it really much lower, and as I increase the amplitude, you should see that the sinusoidal components getting greater. You'll also see more sinusoidal components, indicating that harmonics are being added to the signal. So when I play very soft, it's almost sinusoidal. It's just one or two strong components, but that changes as the trumpet gets louder. And we'll learn about this later in the course. All right, the other thing I can do is just show you, as you might expect, if the frequency goes up on the trumpet, the sinusoidal components are going to move to the right, because they're going up in frequency. So hopefully you saw the whole image sort of shift to the right and back to the left as I went up and down the scale. Another indication that we're actually measuring frequency. So again, we can express the Fourier transform in terms of real and imaginary parts, or amplitude and phase parts. Typically, if we compute the Fourier transform numerically, we get real and imaginary parts, and we have to do a little trig to recover the amplitude and phase part, but they're equivalent. Power is proportional to amplitude squared, and we're very sensitive to power. We're not really sensitive to phase. We can't generally hear it. If you measure a signal and then you measure it again at some time difference, delta t, the amplitude spectrum is unchanged, but the phase is going to change by delta t times omega, the frequency. And so, the fact that the amplitude does not change with time delay is maybe the reason that we're so sensitive to amplitude and we kind of ignore phase, because these time differences are all kind of relative. So I want to say this again, that when you transform from the time domain to the frequency domain, you're computing this integral over time from minus infinity in time to plus infinity in time. So the time component gets completely integrated out. There's no time variable remaining. The Fourier transform is not a function of time. It's only a function of frequency. So get that into your head. It's a common misconception. So this will come up again. Later, we're going to look at short time transforms, which is what you saw on this spectral display. And those are time varying.